So this leads us up to what's called standard enthalpy values. And there's a group in Washington, D.C. called the NIST, the National Institute for Standards and Technology. And people in labs, deep in basements where it's stable and safe, will calculate the standard molar enthalpies of formation. And in the background of this slide, I have a whole bunch of different delta HFs. And you can see, for example, that C3H8 there has a value of negative 103.8. All right. On the other hand, some of them are positive too. So C2H4 has a value of positive 52.3. It kind of depends on which one you're looking at and stuff to do. But anyway, these are all called standard molar enthalpy of formations, or delta HF. And that little f has a meaning. All right. It means that you're making 1 mole of the compound, and you're making the compound from elements in their standard states. There are a whole bunch of different delta HF values, and at the end of problem set 5, or in your textbook, or through Google, you can find these delta HF values, and they're super, super important. Now, elements in their standard states have delta HF equal to 0. So that means that O2 gas would be 0, but not ozone or liquid oxygen. And graphite, the more stable standard version of carbon, would be 0, but not diamond. So elements in their standard states are 0, but all the other things will have their own delta HFs. And using this table is going to be something that's going to be helpful to us here coming up. What's the standard molar enthalpy of formation reaction for potassium permanganate? Okay, so we're trying to figure out here what the delta HF is for potassium permanganate. And what you have to do is you have to first of all figure out what the heck potassium permanganate is. And if you know, cool, and if you don't, no worries. Potassium permanganate, KMNO4. Now, the molar enthalpy of formation reaction would have 1 mole of product and only 1 mole of KMNO4, and then all of the reactants will be elements in their standard states. So K, Mn, and O are the 3 elements here, okay? Potassium is K by itself, manganese, Mn by itself, oxygen diatomic has to be listed as 2. You would need 2 of them. And remember, you can only make 1 mole. So 1 KMNO4 is the product, and all the elements that go into it are the reactants. So it's pretty sweet. The metals and stuff like that are all standard conditions. You want to make sure you balance for just 1 mole, which is cool. KMNO4 in the pure state is kind of that solid purple compound in water. It makes a really cool kind of purple liquid, pretty groovy. Anyway. Here are 5 equations, and tell which equation defines the standard molar enthalpy of formation for gaseous methanol, CH3OH. Now again, because it's an enthalpy of formation, there's 2 things you want to do. You want to have just 1 mole of product, and you want to have all reactants, elements in their standard states. So let's go through here. A has 1 mole of product, definitely, but the reactants, CH4 is a compound, so that's not elements in their standard states. That one's not going to fly. The second one, we have 1 mole of product, and if you look at that, elements in their standard state. So C of solid is usually graphite, 2 hydrogens, half of an oxygen, and that's important. You must have 1 mole of product. And because O2 is a diatomic, you have to use a fraction here. I absolutely hate using fractions, but even I, with my PhD, I have to use fractions at this point because heats of formation are always 1 mole. I would much rather talk about equation E because this one gets rid of all the fractions. However, you no longer have 1 mole of product, so E doesn't count. D has a compound, that doesn't count. C has a compound, that doesn't count. Only B here is the heat of formation reaction.